This is a continuation of a problem done in the video for Taylor and Maclaurin series part 1, where we found the Taylor series for the function 1 over 2x minus x squared, anchored at the point x equals 1, and developed this as the corresponding Taylor series. Now our job here is to find the interval of convergence for this particular series. For what x values will this series converge to that function? We're going to use the ratio test, as we very often do, and this particular setup is not that great for the ratio test. Imagine writing this recipe when we replace n by n plus 1. We'd have 1 plus negative 1 to the n plus 1. And then we're going to divide all of that by this business, which represents a sub n. We're not going to get a lot of good cancellation in those coefficients. So what we're going to do is rewrite this a little bit and see if we can re-index it. Let's just look at the first few terms of this series without the summation. When n is 0, we'll get 1 plus 1 over 2, which is just 2 over 2, which is 1 times x minus 1 to the 0. When n is 1, this numerator is going to be 0, so the whole thing's gone. When n is 2, we're going to get 1 plus 1, or 2, over 2. And then the x minus 1 squared. When n is 3, this will be 0. When n is 4, this will be 2 over 2. So what we can see is the coefficient is always 1. That's nice. And then we have even powers of x minus 1 cascading down the series. So we can re-index this simply as the sum of x minus 1 to the 2n, so that we're only seeing the even powers. This is much better for the ratio test, because I'm going to call this, whoops, I put my n where my quotes were supposed to be. We're going to call that a sub n, and if that's a sub n, then the term that would be known as a sub n plus 1 is x minus 1 to the 2 times n plus 1, or 2n plus 2. And then for the ratio test, we're going to load up the ratio, a sub n plus 1 over a sub n, with the absolute value bars on it, which will be x minus 1 to the 2n plus 2 divided by x minus 1 to the 2n within the absolute values. That just means there's 2 more x minus 1s on top than there are on the bottom. So we get this. Ratio test says, all right, you've built this quotient or this ratio with the absolute values. What are you going to do with it? Well, you're going to take the limit of it as n goes to infinity, which in this case is the limit as n goes to infinity of x minus 1 squared. That has to be less than 1 for convergence. Now, you might think this is a little weird because you're doing a limit as n goes to infinity of something that ended up with no n's in it. Well, that's fine. This is just then x minus 1 squared in absolute value has to be less than 1. That means that negative 1 and 1 are the bounds of x minus 1, which means that we're looking at the interval between 0 and 2. And then remember, check the endpoints. Because at these endpoints, 0 and 2, that's where this limit is equal to 1. That's where the ratio test tells us nothing. And so we basically have to say, all right, at x equals 0, we know nothing about what's going on. So why don't we just take that and go up to the beginning and say, hey, series, what do you look like when x is 0? Well, when x is 0, we get negative 1 to the n times all of this, and that's just going to give us an alternating series of a bunch of zeros and 1s, and that's not going to converge. Okay, so this is x the variable, this is x the no, it didn't converge. At the other endpoint, sorry, for x is 2, when we come up here, and plug in a 2 for x, we'll get 2 minus 1 to the n, so that's 1 to the n, which is 1. Well, again, the 1 times this business, we've got an infinite series of what's a list of zeros and ones, 1, 0, 1, 0, 1, 0. That infinite series is also going to diverge. So we don't get divergence at either endpoint, and this right here ends up being the interval of convergence. And if you're not tired of hearing about it, if you are, that's good, because that means you've heard it enough, and hopefully it's getting to you. This work here is not submittable. This was scratch work that I did to get the problem sorted out. I would then go back, make it neater, put in some actual words as transitions, and put in a proper concluding sentence. To show you this series and its function in action, I'm going to click over to Maple, where I have prepared the function 1 over 2x minus x squared and the first 20 terms of this approximating Taylor polynomial. And here's the resulting graph. Our interval of convergence that we just developed says that, hey, if we look between x equals 0 and x equals 2, we should see the approximating polynomial converging on the function. Now the function is in red, right? There's two asymptotes here, so here's one wing of the function, here's another wing of the function. Over there, at those two places, we're not in our interval of convergence. Between x equals 0 and x equals 2, this is our interval of convergence. We should see the red curve. Well, that's underneath the blue curve. The blue curve is the approximating polynomial, and so to our eyes, we can't even tell the difference between the approximating polynomial and the function. That's pretty cool. So within the interval of convergence, we see convergence. The polynomial is right on top of the function, so well that you can't even tell them apart.